Hey, welcome back. We're going to go ahead and go over this next group of material, starting with Chapter 2. And the first thing we're going to pick up is, well, now we're actually going to talk about probability. Specifically, we're going to be talking about probability where we have equally likely things. We'll see where this changes a little bit later, but all of Chapter 2, everything we're going to be doing here is all equally likely chances. Okay, so here's how we break things up. Let's go ahead and start with something simple. Okay, we'll flip a coin. We have something called a sample space. So this would be our sample space. Our sample space is really everything that can possibly happen. So with flipping a coin, this is really simple. You can get a heads or you can get a tails, right? So it's as simple as that. And what's important here is each one is equally likely. You're equally likely to get a heads as you are a tails, right? Okay, so using that, we want to know what is the probability of a heads, flipping a heads. It's just the number in the sample space that we're interested in. So the number in sample space, or the size of sample space that we're interested in, I guess that we want. How about I'll put 1 all over the total number in the sample space. So this is just how we'll do equally likely probability. You write out the sample space, you look for what we're interested in, probability of heads. So here we see that there's only one possibility of flipping a heads, that's it. So that goes on top. Out of how many in the sample space? Well, we have 2. So this would be 1 out of 2. So our probability of flipping a heads would be 1/2. Let's move on to something slightly more interesting. How about rolling a dice? You could roll a die. And so what's our sample space here? Okay, so our sample space here is we could roll a 1, we could roll a 2, we could roll a 3, 4, 5, or 6, right? These are the only possible things that can happen. 1, 2, 3, 4, 5, or 6. So we'll ask something really simple. What about probability of rolling a 1? Again, so we find the number that we're interested in the sample space over the number total. So how many 1s can we get? We can only get a 1 one way, right? Rolling a 1, right? And how many total are in the sample space? There are 6 here. Again, notice that in this case, yes, there are 6 sides to a dice, and they're all equally likely. So this is why we can do it this way. What about probability of rolling an even number? So we go to our sample space, okay, we see that 2 is even, 4 is even, and 6 is even. So we have 3 even numbers. So we have 3 ways to get what we want, 2, 4, or 6. And then just like before, the total number in the sample space is still 6. So we have 3 over 6, or if you want, you can reduce that to 1/2. Typically, at least for entry on your quizzes and tests and things like that, what you'll go ahead and do is you'll take this 1 over 6, and you'll do 1 divided by 6. So what you'll actually enter is 0.166 repeating. You might round this 1667 or something like that. And then you can do this 1 divided by 2, which should give you 0.5. So these are the actual things that I'll be asking you to enter. And actually, with rolling a dice, we can do some really complicated things with this as well. Okay, so I see that maybe I'll reserve this for later. Interesting to note though, your book mentions this thing called law of large numbers. I'll just briefly go over it. So take this flipping a coin scenario. Law of large numbers. It basically says, well, how does this work? If you actually run this scenario, if you flip one coin, you do it 5 times, you might have 3 heads out of 5 times that actually happen. And that's not this 1/2 that we had gotten before, right? We've gotten 1/2 here for this heads and tails. Okay, so maybe you do this a little bit more. We do this maybe 10 times. So out of the 10 times, we see something like maybe we have 6 heads, so we get 0.6. Maybe we do this continuing it. We get 100. We'll have something like maybe 55 heads. So this would be 0.55. The law of the large numbers just tells you, as you repeat the sample size, this was 5 times flipping a coin, this was 10 times flipping a coin, this was 100 times flipping a coin. As you increase the sample size, these numbers on the right side, these probabilities, or I guess proportions you might call them, just in your experiment, how many heads did you get out of how many total experiments did you run? This is going to get closer and closer to this 0.5 that we're talking about, which is the probability of flipping a heads. So that's all the law of large numbers is. It's saying that you have a larger number, it's going to be closer to this 1/2. Of course, we don't say that exactly half the time we're going to get heads or not. That would be silly, right? Okay, so that covers that. Okay, let's move on now. Disjoint and mutually exclusive. Okay, so what does it mean to be disjoint or mutually exclusive? Let's call event A. Event A is just going to be rolling an even number. Event B, we'll say, is rolling an odd number. How about that? Odd number. So A and B here are what we call disjoint or mutually exclusive. These mean the same thing, disjoint or mutually exclusive. Sort of this kind of scenario. A and B. A is what? It could be a 2, a 4, or a 6. And B is what? A 1, a 3, or 5. These are odd numbers. So we have no overlap. We have nothing that is both an even number and an odd number. We don't have anything that's in event A and event B. So these two adjoints or events are disjoint. A and B are disjoint. Or mutually exclusive. I'll put ME for mutually exclusive. Alright, so what else can we look at? Look at something very simple as far as, let's see, when are they not disjoint? Take event C then. Let's call event C. It's just something as simple as rolling a 2, for instance. How about this? So then we could see that A and C are not mutually exclusive. And these are just very simple events, right? We can see that C, this lies in C as well. So we would have an overlap. Sort of this A is here, this C is here. We'd have 2 in the middle, with 2's in both. And you can do more complicated things in this as well. We'll see if instead we said Well, let's keep it simple for now. How about that? Okay. Let's look at. The book has an addition rule. The book lists 2 addition rules, which is sort of silly in the way I think about it, but let's do one more event. Event A is we've got some cards here. So we've got 52 cards, no jokers or anything like that. And we're just going to draw 1 card and see what happens. So event A is drawing a diamond. The card happens to be a diamond. Event B is having to draw a face card. Are these 2 events mutually exclusive? Okay, so we look in this and say, well, can we have something that is a diamond and a face card? Something that is both A and B. And certainly, yeah, we can have a diamond face card. We could have the Jack of Diamonds, Queen of Diamonds, King of Diamonds. We've got 3 of them. So these are not mutually exclusive. So I think that's another good example. Oh, okay. Let's kind of look at what your book calls the addition rules, or general addition rules, things like that. So I'll go ahead and write the general one down. The general one is the probability of A, or let's write this way, A and B. Let's not do that. Let's write it as A or B is equal to the probability of A plus the probability of B minus the probability of A and B. So then there's this minus sign. There's a couple ways you can organize this. For instance, if I add this probability of A and B here and subtract this probability of A or B, it's sort of the same thing. But let's go ahead and explain it this way. Let's call this A, and let's call this B. So how does this work? A or B could be in this circle or in this circle, right? So let's go ahead and look at probability of A. So we want to add this probability up, right? So we count that, that's probability of A, plus the probability of B. So we count up everything that's in B. So that's all of this. But you notice what happens when I actually do that. I count this space in the middle twice. Right? I already counted it for A. I don't really need to count it for B. So what happens is, because I count this space twice, I have to subtract it off. The space is where we have A and B. So something that's in A and B. So that's this, we subtract off one of these A and B's. So we count it once, we count it twice, and then because we counted this twice, we subtract it off. So this is a nice, simple one. It's just sort of, it's really general. Your book offers another one, just sort of without this part, saying if they're mutually exclusive, this is what we have. But let's look at that. What if 2 events are mutually exclusive? For instance, let's look at this heads and tails. So let's call event A heads and event B tails. Then the probability of heads or tails so we found out the probability of heads, right? Probability of heads plus the probability of tails, and I'll run out of room here. I'll subtract it underneath. Minus probability of heads and tails. So you can see that if you do go through the book, this will kind of simplify to this disjoint one that they have. So the probability of heads we saw was 1/2 or 0.5, either way, it works out fine. Probability of tails, it's not hard to convince yourself, it's the same. We have 1 chance of getting a tails out of a heads or a tails, so it's also that. And what is this probability of the heads and the tails? Well, these things are disjoint, meaning that we can never have a coin flip that's heads and tails. So when you just can't have something, when it's just not possible, the probability of that thing is 0. And that's why there's this difference. If you have something that's disjoint, you end up not having this sort of thing. So do yourself a favor, instead of memorizing both forms, this and then that without it, just know that this works for all of them, okay? So doing this 1/2 plus 1/2 is 1. Probability of 1 just means absolutely it has to happen. That event is going to happen. So if we flip a coin, absolutely we're going to get a heads or a tails. And I know it's silly, but this is just a really elementary example just to show you. Yeah, if we have probability of our sample space here, it's going to be 1. Probability of something that can't happen, it's not in our sample space, is 0. Right? So we saw that here with these disjoints. So let's use this probability to find the probability of an ace or a spade. So we got our cards again, shuffle them up, we're going to draw one card, we want to know if the probability of that card is an ace or a spade. We're dealing with 52 cards here. Right? Okay, so if we break this up, using our formula, this is the probability of an ace, plus the probability of a spade, right? But remember, in doing this, we count that space in the middle twice. We'll go ahead and subtract that off then, where we have an ace and a spade. Okay, so let's see. What's the probability of drawing an ace? Okay, so we're not going to actually write the sample space out. This is large. There's 52 cards here. But it's the same idea. You have 52 cards here. They're all equally likely. So we can play this game. Number of what we want on the top. There are 4 aces in a deck. And what we want on out of how many on the bottom? 52 on the bottom. 4 out of 52. The probability of a spade. Well, in 52 cards, well, there's one suit that is spade. We have 13 of them that are spades. Ace, what is that, 13? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. Yeah, 13 out of 52. And we want to subtract off the probability that our card is an ace and a spade. So you notice that an ace and a spade here, these are not disjoint here. We can't have something that is both an ace and a spade. Let's call it the ace of spades, right? We only have one of them. So the probability of this would be 1 out of 52. So adding these things together, we get 17 minus 1 equals 16 out of 52. And you can go ahead and reduce this if you want. But again, your answers are just going to be, take this 16 divided by 52. This would be 0.3077, or about 30.7%. So this would be what you would put in. Let's see. What about the probability of a heart or a diamond? So this would be the probability of a heart plus the probability of a diamond minus their intersection, minus the probability that we have a heart and a diamond. Oh, that guy. Alright, so you'll notice here, you can't have something that's a heart and a diamond, right? We only have one suit value that a card can take on. So this thing is going to be 0. So you notice that this is 0, that's going to go away, and you have this reduced form of the addition formula they give in the book. Okay, so what is the probability of getting a heart? There are 13 hearts out of a deck of 52. And what's the probability of getting a diamond? 13 diamonds out of 52. So you have 26 out of 52, or 1/2. 1 divided by 2 gives you 0.5. So the probability of a heart or a diamond is 0.5, which seems to make sense. You have four suits in a deck, so these are two of them. So we've got two of them. One hand. All right. So you should kind of notice a couple patterns happening here. First of all, outcomes are disjoint. Every probability that we have, probability of A, is going to be between 0 and 1. If it's 0, it means that it can never happen. Just won't ever happen. If it's 1, it means it happens every single time. So for instance, flipping a coin, what is the chance it's going to be a heads and a tails? 0. The probability that's going to be heads or a tails is going to be 1, because one of those has to happen. We also see that if I sum up all the probabilities of disjoint events, if these are disjoint, this should equal 1. So the way this works with the dice, for instance, we notice 1, 2, 3, 4, 5, or 6 is in our sample space. Rolling a 1, 2, 3, 4, 5, or 6, all these things are disjoint. So the probability of getting a 1 plus the probability of getting a 2 plus the probability of getting a 3, etc. This should equal 1. So this is the whole sample space. This is 1/6, right? 1 out of 6 on the die, plus 1 out of 6 on the die, plus 1 out of 6 on the die. And you continue this. We've got 6 of these. It's easy to see this is 6 over 6 or 1. We won't really use this one too much, but this is really good just to know, just to check your answers. For instance, if you do come up with a calculation where your probability is negative or greater than 1, then go ahead and go back, because it must be that you either interpreted something wrong or punched in something wrong. Okay? Okay, so now I think we can move on to something called the complement. So we talked about these spaces. Let's still use this die. 1, 2, 3, 4, 5, or 6. Right? So event A was we have roll a 1 or 2. So that's event A. So we have something that we call the complement of A. And we'll denote it this way. I think your book uses this little C for complement. All this is defined as not A. So here we have A is rolling a 1 or a 2, so it could be a 1 or a 2. So we want the complement of A. If I were asked to write these out, the sample space of A complement, this is not A, so everything that's not in here, so this would be 3, 4, 5, and 6. So these would be the sample space here. So the probability of A we see is 2 out of 6. The probability of A complement is 4 out of 6. And it makes good sense. We can see here that there's this relationship. If I take probability of A plus probability of A complement, and I add these two together, I'm going to get 6 over 6, which is 1. And this is a good way to remember it. A lot of times people do, you can obviously just take this and subtract A complement from both sides and get probability of A is 1 minus probability of A complement. Or you can do the opposite, subtract the probability of A from each side and get probability of A complement is 1 minus the probability of A. So these, all three are good to know. However, you should be clear that you only need to know one of these things, and you can get the other three. So don't stress yourself out over this. It's just one thing to know. So you could use this if I say complement the A is rolling a 1 or 2, and we found that to be the probability of rolling a 2 over 6. You could use one of these formulas to find the probability of not rolling a 1 or a 2, which is 1 minus 2 over 6, which gives us, what, 4 out of 6. And if you're not good with fractions, again, you can just convert these to decimals. So this would be 1 minus 0.3333, which would give you 0.6666 kind of thing there. So we can see that we have a couple ways of doing this. We're going to go ahead and start making use of these formulas here. But just makes good sense, right? The A complement is not A, so everything in the sample space that's not A. And if I add these two things up, these things are disjoint, they make up the whole sample space. So I should be able to add these things up and get 1, because sample space is everything that can happen. Okay. Alright. Moving on to independent processes. What does it mean for something to be independent? So in English terms, as far as independence, and when we're talking about independence, we're looking at 2 events, or really 2 or more events. And we would like to see if these events are independent. In plain English, it's just, will information about the one event tell us anything about the occurrence of the other event? So if I have this heads or tails thing, if I have event A is heads, event B is tails, if I tell you I flipped the coin, it was tails, well, I know that it wasn't a heads, so that probably is going to change. It gives me information about the other event. So those things are not independent. A or heads or tails there. I guess your book, I don't know if your book mentions this kind of plain English version or not, but it's useful to kind of know. And I guess the way they put it, the probability of A and B is equal to probability of A times the probability of B. If this holds, the 2 events are independent. And if the 2 events are independent, then this holds. So we saw that it's really easy. This heads things, we can check that very easy. Heads and tails are not going to be independent. But it should be easy just based off what I told you. You know, if I give you information that, yeah, I flipped the heads, well, then it's obviously not tails. The idea would be to check this equation and see if this holds. So the probability of heads and tails, well, that's 0, right? Can't happen. Probability of being heads is 1/2. Probability of being tails is 1/2. So we have 1/4 equal to 0. I don't think so. So heads and tails are not independent. And it's quite common that students will get confused between independence and mutually exclusive. They're different things. We can have something that's independent and mutually exclusive, like we have here. Or I'm sorry, not independent and mutually exclusive. We can have things that are mutually So these things are mutually exclusive. So in this case, they were not independent. We can have things that are not mutually exclusive and independent, or things that are not mutually exclusive and independent. So it doesn't matter if it's mutually exclusive. Don't think like that. That's a surefire way to lead you somewhere bad. Okay, so as far as using this, let's go ahead and say we're given this information. 9% of people in the US are left-handed. Now we want to pick 2, so pick 2 at random. And at random here, when we do pick things at random, it's safe to assume that they are independent. So picking these 2 at random, we want to go ahead and see what is the probability that both are left-handed. Another way of thinking about that is the probability that the first is, and the second that we look at is. Well, because these things are independent, we're told these are at random, so they're independent. This is nothing more than the probability of the first times the probability of this, or the first is, times the probability that the second is. Right, this is just using that formula that we just looked at. So we can see that this first is, well, 0.09. That's just probability that they are left-handed. It's 9% that's given to us. Then probably the second is, well, person number 2, they're just another person. They've got a 9% chance of being left-handed. So this is 0.09. So we multiply these things together, we get 0.0081, which is 0.81%. So we can kind of use this information. Let's do one more. Using the same kind of data, what's the probability that both are right-handed? So this is the probability that the first is right-handed, not left-handed, and the second is left-handed. I'm sorry, right-handed. Get a little confused here. Hope that doesn't have an effect on you. All right, so this is, these are also independent because we're picking these at random. So this is probability that the first is right-handed times the probability that the second is right-handed. Alright, but we don't have the probability of being right-handed. We only have the probability of being left-handed. Okay. So, probably a lot of you are kind of looking out there and already telling you the answer. But we can kind of use this formula. You use this complement rule a lot more than you realize. Well, as it turns out, right-handed, that is the complement of being left-handed, right? This is not left-handed, right? It means the same thing. So we're given the probability of being left-handed is 0.09. So the probability of being right-handed, or probability of left complement, there's a C here. You could write this as, well, this is 1 minus the probability of being left-handed. So 1 minus 0.09, which is 0.91. So it's just as simple as, well, yeah, these things are disjoint. They add up to 1. So if I want to find the other one, I just take 1 and subtract off this guy. Right? This is the complement rule. So I see that the probability of being right-handed is 0.91. Factor this. Now we can fill these things in. This is 0.91 times 0.91, which gives me, I'll have to write it somewhere else out here, 0.8281. And that's generally how we'll use this complement rule. And we will use that a lot. Okay, so let's kind of move into some basic conditional probability. So we're moving into 2-3. There's not a whole lot in 2-2. So here's what we've got. We've got some results here, and maybe this is a drug test. There are some results: negative, positive, and whether they had it or not. So whether they had taken it, I guess. So yes or no. Alright, so I'm just going to put some numbers in here. Okay, so here's this kind of information that we have. So let's look at the probability of the positive result. So I guess we're getting into what your book calls, well, I shouldn't say what the book calls, it is called marginal probability, joint probability, and conditional probability. We're going to be mainly doing it off of these graphs. I'll show you there's some algebraic ways to deal with this stuff as well. Positive result. Well, how many positive results do we have? Anytime you get a chart like this, the first thing you should kind of think about is, alright, what's the total positives? We have 16 here. What's the total negatives? We've got 84. What's the total yeses? 17. And the total no's? 83. And so down in this box on the bottom right, I can find the grand total just by adding across. So 84 plus 16 will give me 100. If you want to add vertically, this gives you 100 as well. Right? Or suppose if you're really into tedious things, you could add up each one of these things. All four of these things will give you 100. Okay, so positive result. How many ways can we get a positive result? It's not just a matter of just pick a box, right? Positives, well, they could have had it in their system or they could have not had it in their system. So we have to look at both cases. This is just positive results. We had 16 out of how many? 100. So we have this proportion, which is just 0.16. So that's a probability of getting a positive result. And you can kind of see, I could ask things like, what is the probability of not having it in the, not taking the drug, or not having took the drug? So the probability of not having took, we see, okay, so how many are there? First of all, we find, okay, these are the results up here. Okay, this is the information about having took it. So we have yes, they took it, or no, they took it, or no, they didn't, sorry. So we're interested in this, right? We're interested in not having taken it. So how many total did not take it? 83 of them, right? That's why we added across. We have the total 81 here and 2 there, so 83 of them did not take it. Out of how many? 100 still. So this is 0.83. This is called marginal probability. In the first case, I looked at these positives. I added these up and got 16 out of 100. Again, just because the results are up here. So you find whatever column you're looking at, add them up, divide out the total. That's all it is. Next, we'll look at these things called joint probabilities. So I could ask you something like probability of a negative result, and yes, they had it. So this is a little bit different. We want both of these things to be true. Negative result, though, that's this column, and yes, they had it. Well, yeah, it's this row. Where do they intersect? The only place where we have yes, they had it in their system, and it was also negative, was this, right? We have 3 of them. So this one is actually, should be the simplest one, where we have both, right? I got yes, and I've got the negative. So, yeah, it's just going to be this 3 out of how many? Well, we're asking about the total, right? So we still use 100. Alright, so this is 0.03. So marginal probability is this simple, really simple thing. The probability that they had taken the drug and tested positive for it. Again, so this is took and positive. So yes, they took it, and yes, they were positive. It's 14 out of 100. So we have 14 of them that did both. Okay. Now we can kind of start to get into conditional probability. Okay. So, what's the best way to describe this? I guess I'll start with this chart. Let's start with some notation first, though. Probability of A, we've got this line here, B. This means probability of A given B. So this is conditional probability. This is just a matter of notation. So you know when you see in the book, this is really what's happening. So what's given to you? B happened. B happened. So what's the probability of A after B happened? So here, let's look at this. Probability that no, they didn't take it. Given that it was a positive result. Positive result. Okay, so this is a little bit different from what we've been doing before. So this is sort of a false positive. So they ask you something like, what's the probability of a false positive? It means that, yeah, they could get positive results given, or I guess, be more specific in this, not just a false positive, but they were innocent and had a false positive. So, okay. So it didn't take it, given that there's positive results. Don't worry about that. So here's how this works. Okay. So we had a positive result, right? This is given to us. This happened. So this is the only thing I'm looking at. I'm only looking at this box. Positive happened. So ignore everything else. Okay, so now, looking at that, that's what happened. That's what we have to deal with. What's the probability that they didn't take it? Well, this is yes, this is no, right? And this is the total. So, how many didn't take it? 2, right? So this would be a 2 out of 16. So I know this is a little bit different. So this is what, 1 out of 8, or I think 1, 2, 5. Yeah, 0.125. So that's how we would do something like that. Let's look at one more probability that they get a negative given they had taken it, took the drug. So this would be a false negative, given that they had actually taken this drug. Alright, so looking at this, okay, they took the drug, right? So where's the information on this chart where they took it? These are results up here, so we're looking at these two things. So I'm looking at, yes, they took it. So I'm only interested in that yes, they took it. So of that information, we have 3 were negative and 14 were positive out of 17 total. So yes, we took the drug. This is what we're dealing with now, not with this total 100 or anything like that. How many are negative? 3 out of 17. Right, so 17 is there. Divided by 17 gives us this 0.1765. Okay. And so that's just using this chart thing now. Your book has this formula in here, which basically goes like this. Probability of A given B is equal to the probability of A and B, there's an ampersand, A and B, all over the probability of B. This is your conditional probability. This is really what we had just used. You can go back and convince yourself of that. We did just use this. We looked at what are both out of just that one thing that had occurred. It's really easy to kind of see this pictorially. So this is A, this is B. So we're told B happened. B happened, right? So I know something was going on inside this circle, right? Where my dot is, somewhere in this circle. So what's the probability that A could happen, given that I'm in this circle? Well, it's what you want out of what you've got, right? So what you want is for it to be an A. The only way that can happen is if it lies in this space, which is the A and B, probability of A and B. Out of how much? Well, the whole thing is the probability of B. So this is really the same thing that we've been doing before, probability of what you want, that actually lies in A as well, over the whole thing, probability of B. So this is something that's nice to get familiar with. Okay, so we've got a little bit left. I guess we should do these charts the book has. Let's do a really simple one real quick. So we're told that the probability of, so this is maybe a drug test as well. So probability of being positive and not afflicted is, we're told, is 0.03. And we're told that the probability of testing positive is 0.15. So we would like to know the probability of not being affected or afflicted. Spell here. Given that we tested positive. Okay, so this is really quite simple. We're told that we had this positive test. Maybe we don't want this thing. What's the probability that I actually don't have it? Right? So we think about, okay, what's the possibility that both of these things can happen? Probability of A and B. We're given that information, right? Probability of positive and afflicted is 0.03. Let me be a little more clear in this. Probability of positive and not afflicted. All over the probability of positive. This is just using this definition. Okay. So we had, we were given that this top thing is 0.03, and given that the testing positive is 0.15. Go ahead and use these out, and you should get 0.2. Right, 0.2. So you have a 20% chance that, you have a false positive. It's not a very good test then. So this is how we use this conditional probability. Now, there's all sorts of ways to do these things. I guess let's go ahead and look at page 74. And I think there's one thing I particularly wanted to go over. Oh, by the way, your book does not write it this way. I suppose your book writes it a different way. They write the probability that A and B is equal to the probability of A given B times the probability of B. If you multiply both sides by a probability of B here, you see you get the same thing. But this is a lot easier to explain with a picture. So again, it's like you can have a bunch of different forms here, but you only need to memorize one. You might have to manipulate it a little bit, but you should be familiar with a little bit of these different forms. Okay, so page 74 here. I might make one up here real quick. All right, so let's go ahead and say, okay, we've got kind of result. We could live or die, and we could be inoculated with a virus. Yes or no. So that's the situation. You got you could live or die, and you could be inoculated with the virus. So here's the situation. The probability that you live, we're going to go ahead and say is 0.0382. I'll change this up a little bit from the book. The probability that no, you are not inoculated, given that you live, is okay, I'll change these numbers up a little bit. Let's go ahead and say 0.4. And let's go ahead and say the probability that, yes, you were inoculated, given that you died, is probably really high. Let's go with 0.8. Actually, let's make smaller numbers. Let's use 0.03, 0.4, 0.8. Alright, so they've got a chart here that they'd like you to learn how to figure out to make. It's sort of like this. So you start here. Well, let's see what can happen. Well, we could have, what? We could have lived or died, right? So we could live, or we could die. So they break this up this way. They say, okay, we've got living was 0.03. Well, what's the probability of dying then? Again, only one of these things can happen, so you can use your complement rule. It's just going to be 1 minus 0.03, right? Dying is complement of living, right? So 1 minus 0.03 gives you 0.97. And then from there, we have two options for each one. If you lived, well, it could have been that you were inoculated. Yes, you were inoculated. You had this virus. Or no, you were not inoculated. Same thing here. If you died, could have been, yes, you were inoculated, you died from the virus. Or no, it just happened to be a coincidence. You just got hit by a car or something. Okay, so going back to this. Alright, so probability of no, given that where you lived. Okay, so we see in this branch, we've lived, right? So given that we lived, probability of a no is 0.4. Well, we can do the same thing. Well, 0.4, from here, from this branch, we've got 0.4 is no. Well, yes must be 1 minus 0.4, 0.6, right? And then we can look at this dying. Okay, so if we died, So probability of yes, given that we died. So we died, this is given. Now going to a yes, we're told is 0.8. So let's go ahead and fill in the other. It's going to be 1 minus 0.8, or 0.2. So all of these things here, what this means, this is the probability of living. This is the probability of dying. This is the probability of yes, given that you live. This is a probability of no, given that you live. Probability of yes, given that you die. Probability of no, given that you die. It kind of goes in order here. Now, what you can do from here is you can kind of multiply across these branches. Let me kind of do that with you right now. 0.03 times 0.6, we get is 0.018. This is the probability that we live and had it and inoculated and yes. So notice the difference. These are conditional probabilities. These are joint probabilities. Live and yes, right here. What is the probability of no and we live? That's no, we didn't have it and we live. We just multiply straight across. So we get 0.012 is the probability that live and no. Alright, continuing on down. What's the probability of dying and yes? And what's the probability of dying and no? So you have this 0.97 times 0.8. Just moving straight across, 0.97 times 0.8 gives you 0.776. So it seems like a lot of people had it and died from it. That means 77.6% had it and died, right? Let's do the last one, 0.97 times 0.2 gives us 0.194. And so this is just an example to build this tree diagram. Everything you can do without building a tree diagram, but I think a lot of students have kind of told me that it's helpful for them because it almost looks I guess chronological, I suppose, given that they live, what's probability of yes, and just multiplying straight across, you get these joint probabilities. You can use, so all this stuff came from just these 3 pieces of information. So we have all these different probabilities here. It's quite a bit. What if I wanted the probability of yes? Yes, they were inoculated. Yes, they had it. You can see it's not very obvious to use this information to find that. But if you make this chart, you can kind of fill in this information just like we did. Probability of yes is equal to, well, we've got on this right part, we've got this had a bit of yes in it, and this had a bit of yes in it. So it's going to be probability that live and yes plus the probability of die and plus and yes. Now, without getting into too much theory here, this happens because these things are disjoint. And so we just add these things up, though. Plus 0.018 gives you 0.794. So there's almost an 80% chance that these people were afflicted. This was pretty outbroken place. yeah, so I suppose this chart is really nice, and I think you can look into the book. It explains it pretty well, I think, as far as how to use it. That's about all we're going to cover today. So don't worry too much about this chart. You should just know how to make it. Most of the stuff we're interested in is these independents. Know how to check for independence. Really what it means in English, and then mutually exclusive events as well. Know how to draw out your entire sample space and use this kind of idea of equally likely things to find these proportions. You should know these sorts of things as well. Marginal probabilities and joint probabilities, how to do these from a chart. Definitely know how to do these things from a chart. We spent the most time on that, I think, so definitely know how to do that. And as well as your complement and your addition rules. Alright, so I hope that helps a little bit, and I'll see you next week.